Okay, good afternoon, students. We have a midterm exam coming up Thursday after the spring break, I believe. Is that correct? And so we are going to be talking about Chapter 11 stuff today with the solar energy concepts, fusion concepts, and probably a little bit past Chapter 11 into Chapter 12 after on the Tuesday after um, spring break. Okay, so um, here's our outline for the day. By the way, it's a new month, so I'm giving you new quotations of the day from a new source, Will Rogers, who was kind of a humorist and commentator back in the 1930s during the Great Depression. A very famous guy. And he gave a lot of grief to politicians in Congress, as this particular quotation indicates. But he was a very interesting guy, so we'll look at his quotes this month. Okay, clicker questions. A few questions about leap year. So turn on your clicker. Yeah, this thing is a radio frequency, so you don't have to, it's not like your clicker at home where you have to, kind of aim it up here. I mean, you can do trick shots. It's like a cell phone, man. You can be out in the hallway and stuff. Yeah, leap year. Yesterday was leap day, the 29th of February. And you know what? Believe it or not, the 10 years that I've been here at UCF teaching astronomy, so that's roughly about 10 times I've taught it, I have never taught once about leap year. So let's do a little bit about leap year today. Question 1. Uh-oh. I didn't give you any options here. Yeah, it's coming here. All right, there you go. There's your 4 options. 15 seconds to finish. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Hopefully this is easy money for everybody. Yeah, 94% of you. Yeah, leap year is every 4 years, except for years that end in 0, 0. So like the year 2000. And I think there's one other exception involving the number 400. But anyways, this year was leap year. Every 4 years we'll have another one. Purpose of leap year, what is it? This one's maybe a little harder. And we're going to go into the exact answer of this one. You cannot vote for F because F, you cannot stay one step ahead of Chuck Norris. Don't even try. But you can vote for A, B, C, D, or E. Okay, 15 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, hopefully this was an easy one for you. Let's check to see what you guys voted for. Yeah, most of you got this one right. The whole idea is keeping the calendar in sync. Now, notice in this that I did throw in some terms that we haven't talked about evading taxes, but we have talked about the distance to the moon. We have talked about isotopes in SMOW, magnetic fields of Earth and Jupiter and stuff. We have talked about, so don't let that distract you away from the true answer. So let's go ahead and talk about why leap year is necessary. And we're going to make some notes first, and then some diagrams that hopefully will make sense to you. Now here's the whole problem with leap year. Our planet spins at a specific rate, 360 degrees every 24 hours. The problem with that is that the year is a little bit longer than that, about 300. It's an integer number of days plus 0.25 approximately. And that's why we have to add in. So now, today's the first day of March. Okay, March 1st. So if we were to look at the sun at noon, or think of looking at the sun, I mean, I don't want you to look at the sun because you'll burn your eyes out. Okay? But if you were to look at it toward the sun, or figure out the position of the sun at noon on March 1st, you'll approximately be looking at the constellation Aquarius. Now let's say that you're looking specifically at one of the stars of the constellation Aquarius. And this white area here with rectangular borders and corners, that's the official area of the constellation Aquarius. For an astronomer. In other words, we use the different constellations of the night sky to name the stars that we look at. And Sigma Aquarii is right here. All right, right there. So it's right near the path of the sun. This light blue line is the path of the sun through the constellation Aquarius. And then here's Capricorn down here. And then in a few weeks, we'll be heading into Pisces, etc. Here's some of the other ones that are outside the zodiac. These ones down here, they're in the southern hemisphere. These ones up here, Pegasus, that's a northern hemisphere constellation. Anyways, so let's say that, on March 1st, we're looking exactly at this. Now, you could figure out exactly which star that you're looking at from Orlando at noon on March 1st. And let's say that that star is this one, Sigma Aquarii. Okay? Now, that's almost halfway across the official zone, the official Aquarius zone. 365 days later, it's not going to be facing the exact same direction. So 365 times 24 hours from then, it's not going to exactly be facing back towards Sigma Aquarii. It's because it takes approximately 365.25 days to get all the way back around. All right, so in 365 times 24 hours, you're just a little bit looking slightly away at noon, anyways, from Sigma Aquarii. Now, I'm going to give you a diagram here. All right, you can go, if you haven't finished this little outline of notes, let's go ahead and make a sketch. You can catch up with the outline on YouTube later today. Go ahead and make a sketch here. This is a circular arc. I made a big 2,000 pixel circle and then moved it upwards. Let that represent the path of the Earth. Here, down here, this round object that's kind of light blue on the side facing the sun. This is the direction of the sun. And Sigma Aquarii. They're in this direction. And this is us at noon. March 1st, and we're in the middle of the day side of the Earth. That means that right here, the tip of this yellow arrow, that is the location for which the time of day is 12 noon. Exactly. All right? And what I'm saying is that if this is where we look at noon, and first thing you see is the sun, and then behind it, the way the zodiac works, you say that we're in the time of Aquarius, means that the sun is right in front of all the stars in the constellation Aquarius. okay, or a few of the stars of the constellation Aquarius. So we're saying that right now, on March 1st, you're right in front, the sun is right in front of Sigma Aquarii. So if you had X-ray vision and you were impervious to the brightness of the sun, and you look straight at the sun, and then with X-ray vision, you look straight through it, you'd see Sigma Aquarii. Right? So let's say that this is where you are. And so this is the direction that you're looking, this yellow arrow. Make sure you make this circle down here to represent Earth and kind of shade it in with dark shading on the night side of the Earth, okay, facing away from the sun. And then leave it, kind of light over on this side. That's the day side. And I made it light blue. This part I made dark gray. And then this is the direction of observation for you if you look straight to the south at noon on March 1st. All right? So now I'm going to ask you to draw another picture just like this, the next page of your notes or wherever you want to put them, 1 year later. Now 1 year later, you're almost, this is where you're looking. 365 times 24 hours later, you're actually, if you were to look in the south, you'd be looking this direction. And that is why we say it takes 365.25 days of the year to get all the way around. Right? This is 6 hours. What time of day is it right here where my pixel is at the tip of this yellow arrow? It's not noon. What time of day is it? 3 o'clock in the afternoon? What time is it? Is it morning or is it breakfast time or is it supper time? It's breakfast time. Because well, I didn't tell you this, but this is looking down from the aspect of the North Star. So the Earth spins this way, all right? So this tip of this arrow, 6 hours from now, is going to be right at noon. But by that time, the Earth has also moved a little bit around its orbit. So it's not totally lined up at noon. These guys over here, so let's see, a quarter of the Earth away from us. So that'd be 90 degrees from us. So somewhere over in, I don't know, like Israel or Saudi Arabia or someplace like that maybe. They'd be looking at Sigma Aquarius directly at noon. But we wouldn't because of this quarter of a day. Now that's 1 year later, right? And so, oh, I gave you the answer to the question. Yeah, it's dawn. So, right, I forgot about that. So right here, this is dawn. And to look at the sun, you look along the horizon in this direction. And if you're looking straight to the south, you're looking out here in this direction directly to the right. So you're looking at stars if you're looking at south. But if you look east, you'll see the sun coming up. By the way, just so you know that this time of year, if you're back on this side of the earth, so this is supper over here. The tail of this yellow arrow is supper time. Okay, the tip of the arrow is breakfast time. Okay, so after supper, you will have a very good view of Orion, Taurus, Castor and Pollux, the Gemini twins, Pleiades and stuff back here. Every night I get home, if I get home late, I always look up, and we've been having a lot of really good clear nights. And some of you have gone to the observatory. Raise your hand if you went last Thursday. Wow, nice, very good. Apparently it's yellow status right now. Is it tomorrow night or Thursday? Wednesday night. Okay, so tomorrow night, Wednesday night is yellow right now. Hopefully it'll go green. And if you can go tomorrow night, do all your observations, hand in your handout. Ching! That's another 10 dineros. How many people maybe I shouldn't ask this. How many people have gone more than once? Sweet. All right, so you guys are racking up the dineros. And I want everybody in here to rack up some dineros, if you can. And if the weather cooperates. You never know. Okay, so questions about leap year. Okay, let's keep going. Let's talk about energy and luminosity. This image in the background is a false color ultraviolet image of the SUN. And there's a website. I don't have it in the lecture today, I don't think. There's a website where you can always look this up. What the sun looks like in ultraviolet, as well as visible. And a lot of these bright areas here indicate heat. It's really hot. And so you're getting a lot of high energy ultraviolet from these areas. And then other areas are dark. And so analyzing that, scientists can analyze sunspots and stuff like that. Okay, so I'm going to trot you through some of the basic energy units of the metric system. The metric system energy unit is called the joule, the main energy unit. So, for instance, now an exception of that, the calorie, like the food calorie, so many calories for a plate of shrimp, so many calories for, what, don't you ever think of a plate of shrimp? You don't? Why not? A lot of people. A lot of people, you're doing something and all of a sudden you're thinking about a plate of shrimp. You've never experienced that? I've never wanted. That's from a movie, man. I'm burning your grits. That's from a movie from the '90s, Repo Man. And the guy that said it in the movie, the guy he was talking to, had the same reaction that you did. What are you talking about? Anyway, so the exception to the metric system energy unit is, or an exception, I should say, is calorie. Okay, the food calorie. So any kind of food, whether it's a plate of shrimp or a donut from Dunkin' Donuts. Now, don't tell me you never think about that. Pizza, any kind of, celery, soda pop, high fructose corn syrup, what your mom tells you not to consume. Calories are an energy unit. Okay, and there's other energy units like the BTU, stuff like that. But we're going to talk about joules. Now, the joule, here's one way to calculate it. It's the kinetic energy of a 2 kilogram object that's moving at 1 meter per second. All right, now the formula for kinetic energy in general is 1/2 mv squared. So if you have a mass of 2 and a speed v of 1, 1 squared is equal to 1. 1 times 2 is 2, and then 2 times 1/2 is 1. So the kinetic energy of, let's see, what's a 2 kilogram object? It'd be about 4.5 pounds. Like if you're putting in a muffler or something, or a bicycle wheel might be a couple kilograms. Anyways, so 4 kilogram object. And so we're going to be talking about the energy burning off the sun. So we're going to be talking about joules. Now, it happens at a certain rate. And the energy dissipation rate, or the power, or in astronomy terms, the luminosity, is measured in watts if you're using the metric system. And there are other measures of luminosity. Like, for instance, if you go to the store, they rate light bulbs, I think, in different units of luminosity. But 1 joule per second is a watt. So, for instance, an incandescent light bulb like this one over here, 60 watts. And that basically tells you how many watts of energy it draws from your electrical system when you turn it on. Okay, 60 joules a second. And so what you pay for at on your power bill, if you pay your power bill at your apartment or your home, you're paying for kilowatt hours. So that's 1,000 watts times 1 hour. And an hour is 3,600 seconds. So 3,600 times 1,000 is 3,600,000. So a kilowatt hour is 3,600,000 joules. Okay. Anyway, so a light bulb is 60 watts. The sun is 3 times 10 to the 26. Whoa. That is a lot of wattage. All right, now 26, 10 to the 26. Okay, 10 to the third is 1,000. 10 to the 6 is 1,000,000. 10 to the ninth is 1,000,000,000. Trillion. Quadrillion. 5,000,000,000. 6,000,000,000. 7,000,000,000 is 10 to the 21. 10 to the 24 is octillion. So this is 380 octillion watts for the SUN. That's a lot of power. And I'm going to try to put that in perspective for you. Now, in a few minutes, we're going to try to figure out the solar, how much of the sun is converted into energy per second. We're going to try to work that out today. Now, another thing that I want you to make a note of, we're not going to talk about it directly today, but maybe after vacation in chapter 12, is apparent brightness or apparent luminosity. So, for instance, if you have a 60-watt bulb that's 2 feet away from your nose, it's going to burn your eyes out. But if you're looking at the sun from 2 light years away, it's not going to look very special at all. It's just going to be a star. So the distance as well as the absolute luminosity factor into the apparent brightness of an astronomical object. And it is something that we're going to deal with probably after vacation. But I want to introduce it now because it's a natural point to introduce it. Now, last thing I want to recall to you is the solar constant. Now, that's not in watts, it's watts per square meter. That tells you the density of the energy rate. In other words, how dense is the wattage or the apparent wattage at the distance that you are standing. So if you're standing 500 light seconds from the sun in pretty much any direction, you're getting 1,367 watts for every square meter. Now, a square meter, the front of this lectern is about maybe 2 square meters. I don't think it's square, but if you actually measured it, it'd probably be about 2 square meters if you measured it carefully, all right? So the front of this lectern would catch about 2,700 and change watts, okay? Now, let's talk about some other stuff here, all right? Here's some other examples of energy. All right, and this is stuff I was looking up on Saturday afternoon, trying to work out some stuff that you can get a handle on. Okay, a Camaro, 2016 Camaro, quarter mile. In 12 seconds, it reaches 115 miles an hour. All right, that's about 50-something meters per second. If you work out, you look up the mass of the Camaro. It's about, I believe it's about 1,500 pounds. So many kilograms. You can figure out the kinetic energy, 2.2 million joules. So the 1/2 mv squared for this 2016 Camaro at a quarter mile is 2.2 million joules. The symbol for that is capital M, capital J, megajoules. All right. Now a tank round over here from an M1A1 Abrams tank is now this is the gases that expand out of the tube of their rifle, but the actual projectile of their armor-piercing round is a big tube of depleted uranium. So it's really heavy, but it goes really, really fast. And I looked up the specs for it, and it comes in at about 12 megajoules. So it's a little bit more. Can you imagine that? A little hunk of uranium, and it's got, almost 6 times the kinetic energy of this baby going 100. So just think about that. If you, that's a bad example. If you saw a Camaro going at 115 and it plowed into I'm trying to think of something. I would normally use Justin Bieber, but I don't want to be a hater. But if you saw if you saw a Camaro at 115 plow into somebody's house, bam, that house is going to be a lot. It won't destroy the house unless it's a small house. Well, it could destroy a small house, but it would definitely destroy a lot of the house. And the reason I bring that up is there was a news story on Channel 9 Eyewitness News last week of some lady that she lives by a street where apparently a lot of people speed, and occasionally, and she's twice now had people land in her living room with their car, totally demolishing everything in her living room and stuff. So it can happen. So just think what this thing would do, hitting somebody's house. Now, compare that to this, hitting the side of another tank. That other tank it's out of here. It's going down like Chinatown. All right. Now, but of course, the Navy has to be superior. So look at there. They got a hypervelocity projectile from their railgun. Nice. 32 megajoules for that. So now you're talking about taking down not another tank, but you're talking about taking down a naval warship with something of this. And all this is probably is a piece of, well, I don't know. It might not be uranium. It might be made of iron. But no matter what it's made of, at 32 megajoules, you're getting a lot of damage, whatever it hits. Now, if it goes into the ocean, of course, it's just going to kill a few fish, I guess. But if this hits a naval warship, the naval warship it's going to be either, maybe if it's an aircraft carrier, it won't be demolished, but it'll have a pretty big hole in the side of it. And if it's a destroyer, it'll probably be demolished. It'll be sunk. So they're trying to outdo the Army on that. All right, now we talked about the luminosity. That's basically a power rating for a star or for anything. So many watts. Now the Camaro has at a quarter mile, 150 miles an hour, kinetic energy of 2.2 megajoules. To develop that in 12 seconds, from 0 to quarter mile, so standing start as fast as you can for a quarter mile, you're at 115, It takes 12 seconds to do that. Anybody in here have a Camaro? Like a Bumblebee Camaro? Man, I wish I had one. Anyways, because look at that speed. Anyways, so you get it up 12 seconds, 150 miles an hour. And so that gives you a power rating. And the power rating is 176 kilowatts. That is a pretty nice amount of power. Okay, I have a question for you. And this is in relation to Florida. Raise your hand if you, or at your home, or maybe your parents at their house, have a electrical generator for emergencies like a hurricane. Anybody? Okay, now raise your hand. Okay, put your hands down. It's a bunch of you. Now, raise your hand if you know the kilowatt rating or the wattage rating of that generator. Anybody know it? It'd be interesting. This Camaro has got a big engine. Big engine. All right. So it's going to have a lot more power, a lot more kilowatts than one of these little generators. Okay. So I'm guessing that, and I'll have to look this up, a generator for home use in a hurricane or something is maybe going to be a few kilowatts, maybe 5 or 10 kilowatts, a good one. But I don't know for sure. I'll have to look that up. Now, I did look this up at the Sally's Beauty Supply website. They have a hairdryer that's almost 1,000 times smaller than this. So the Camaro's coming in at 176 kilowatts, hairdryer 1750 watts, 1.7 kilowatts, very common. And actually that tells me that a generator set for home use, it's got to do more than just a stupid hairdryer. So it's probably not 176 kilowatts, but because this is like 1.7 kilowatts. So 1.7 kilowatts would be pretty pathetic for emergency duty after a hurricane. So I'm guessing maybe upward of 10 kilowatts. Anyways, I'll try to look that up. Okay, so these are some everyday things, but there's no way. I mean, if you look back at your figure for the SUN, 10 to the 26, 8, that quadrillion, wait a minute, octillion watts. This is, as much as this is, a rail gun is going to develop this kinetic energy in a fraction of a second. That's how it works. And they probably don't disclose that. But this is going to have a really high power rating, this railgun device. Same thing for the M1 Abrams. In a few seconds, the armor-piercing part of this round, from the inside of the tank to the exit, the muzzle velocity, so that's about, I don't know, 3 or 4 meters, maybe 5 meters. A few fractions of a second develops 12 megajoules. These things are going to have a big power rating, but nothing like the sun. So let's talk about the things that control the power of the sun. And to do this, we're going to start with a couple of questions that you will need to use your iClicker for. So get your iClicker out. In the battle between gravity and fusion, gravity is paper and fusion is a rock. Yeah. So yeah, so I was right. I was in the right area. About 10 kilowatts is what I was thinking. Thank you for looking that up. The student up here in the front said she just looked up the average home energy use, about 11 kilowatts. So to power a home, you would want, somewhere 10 kilowatt for your home generator. Okay, clicker question number 3 today. What happens when you press your hands together and rub vigorously? So this is kind of like an IQ test question. I know it's going to be very difficult, mentally challenging. Hopefully you'll... See, this is a picture of Roy G. Biv. Look at that, when he was in high school. Come on, 1982. What are you talking about? All right, 10 seconds to vote. Ten, nine, 8, 7, 6, 5, 4, 3, 2, 1, 0. Let's see if you guys can figure it out. Yes. What? Somebody voted for C, and actually, uh, two people. No, don't laugh. Don't laugh. That's not a. I mean, the Brittany thing here is, of course, is spurious. But actually, if you were to rub them hard enough, they would emit Roy G. Biv light. But you can't get your hands that hot. You're talking, a few thousand Kelvin, and you're not going to. So this is, it's wrong, but it's not as wrong as B. So there's of course, your correct answer. And this is one of the things that gravity does for everything, really. And for a star, this is the source of its initial heat, is friction and just pressure. All right, next question. Which object heats up more from gravitational compression? Large mass or small mass? 20 seconds to vote. This is a traffic jam in China, supposedly. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Let's see what you guys got here. Ooh, interesting. Which one heats up more? Most of you voted for A, and the actual answer is A. Okay. Good. All right, let's keep going. Gravitational compression. This is what we believe forms planets and stars. If a big clump of material, if it's big enough, Shannon, that if it's big enough, it'll form a star. If it's not quite big enough, it might form Jupiter or maybe something a little bit smaller like Earth. Okay, the heating is significant during this process. And so we can look out in the universe and see sources, Leland, Carlson, that are emitting a lot of infrared, but they're not stars. Those are we think those are baby stars. In other words, they're not born yet, but they're in the process of getting bigger and bigger, hotter and hotter, and eventually they'll start a nuclear reaction. Okay? Gravity is not enough to produce this level of brightness, this much luminosity. And that is because the gravitational interaction is very, very weak compared to the nuclear interactions. It's also very weak compared to the electromagnetic interaction. So the force, for instance, between Leland, between a proton and an electron, there's gravitational force pulling them together, and there's also electromagnetic force, opposites attract. The electromagnetic force is enormous compared to the gravitational force. But the thing about gravity is it can never be shut off. It always is working. But the nuclear reactions in the center of the sun have not always been there. The sun has always been gravitating. The universe has been gravitating, but we don't always get nuclear fusion reactions in the core. Now, I'm telling you that it's really hot and you get it by rubbing your hands together, or the equivalent gravitational of, and you can't get heat. The more heat you get is from really pressing hard. If you just kind of wimpily, in a wimp-like manner, press them together, you're not going to get much heat. But if you really press them together hard, you're going to get a lot of heat. So let's talk about the temperature scale. All right, and we've talked about this a little bit before. Let's review it. The Kelvin temperature scale. This is the one that we use. We're talking about stars and planets and stuff, nebulas, galaxies, Kelvin scale. All right. Now, here's Fahrenheit that we know about. It's oriented to the freezing point of water and the boiling point of water. 212 Fahrenheit, 32 Fahrenheit for the boiling point, and then the freezing point. Now, over here is the Celsius scale in the middle here, and that also is oriented by design to the boiling point and the freezing point of water, and it uses 100 degrees. It's the metric system, so they decided to make it a decimal. So they could have done 10 degrees, but they decided to do 100 degrees of separation. Now notice that the difference, the degrees of separation from freezing point and boiling point on the Fahrenheit is 180 degrees. That is not accidental. Okay, so Professor von Fahrenheit back in the day, I think it's late 1600s, chose this degree size. So 180 degrees of separation Fahrenheit, 100 degrees of separation in the Celsius. Now the Kelvin scale is over here. The freezing point is 373, the freezing point is 273, the boiling point is 373. Now again here, on this one, there is 100 degrees of separation, or as we say, 100 kelvins of separation in the Kelvin scale between freezing. But the 0 point is not the freezing point. Celsius, yes. The 0 point is what we call absolute zero, and it's way, let me get my cursor back here. All right, the 0 point of the Kelvin scale is way down here, and that's the supposed point at which all kinetic energy is kaput. We think that as for instance, a gas, in a gas, we think of the molecules as zipping and zapping around, random directions, random speeds, but they have an average that controls the temperature. And so the higher the temperature, Fahrenheit or Celsius or Kelvin, the more kinetic energy on average a molecule will have. And that kinetic energy can do work. So up here, you can do, especially up here above 212 and 100 Celsius, you can have a steam engine, for instance. And you can have any kind of a heat engine in which you have two objects, one of them's cooler than the other. Now, once you get down to this level of coolness, you can't operate a heat engine anymore. So that's why it's called absolute zero. And a colloquial way of thinking about this is that molecules stop. They do not stop, because quantum mechanically, they're quantum mechanical waves and they're still waving. But they have finished their useful life, or they have paused their useful life until they warm up again. And we have never, theoretically, it is impossible to get an object to cool something to 0 Kelvin, because to cool something to a lower temperature, you need something that's below that temperature, and you can't get below 0. So we've gotten really, really close to 0 Kelvin, but we haven't, theoretically it's impossible to get right to it. But this is where it is. It's 273 Celsius degrees below the freezing point of water. Okay, so that's 2.7 times the separation between boiling point and freezing point in the Celsius scale. And so that makes it 273 and 373 here, and then 0 down here. Now, we're going to be doing a lot of talking about Kelvin scale. We're not going to talk about Celsius, And we're for darn sure not going to be talking about Fahrenheit, but this is where it is. I mean, this is the stuff. We're not going to be converting anything. If I give you a temperature to work with on a test, it's going to be in Kelvin. You won't have to worry about converting, but you do have to know, kind of where it came from and, what is hot on a Kelvin scale. And so if it's hot on Kelvin, it's going to be, so 273 Kelvin is cold. You'd be freezing your what off at 273 Kelvin. But 373, yeah. The surface of the SUN, go ahead and make a note of it. The surface of the SUN, what we call the photosphere, is 5,800 Kelvin, 5,800 K approximately. Sunspots a little cooler. That's what makes them. Yeah, they're a little cooler. They're a little bit less luminous, so they look dark. They're still pretty hot though. So they've dipped a little bit below 5,800. So 5,800 is way up here. 5,800 Kelvin is way up here. It's way up here above Celsius. Is way up here Fahrenheit. But we're going to work in Kelvin. So here's the specs on it. It has Celsius degrees. It's not oriented to the freezing point, but to the absolute zero of molecular motion. And there are still 100 kelvins between ice and steam. And it looks like I misspelled the word "and" here. Sorry about that. I'll try to change it before we podcast it. And just to let you know, we're going to be talking about Kelvin temperatures of stars. And let's start doing that. It's a picture, a recent picture, not too long ago, not too many days ago, of the sun's atmosphere. Looking at this wavelength of light, so write down 304 angstroms, and that means that you've got plasma at 60,000 Kelvin in this range. So plasma at 60,000 to 80,000 Kelvin is going to generate a lot of ultraviolet at this wavelength. So this is a filter that they put on a telescope, and then they take a snapshot. Now, it won't expose color film. So what they do is they take the different intensities and they give it a different degree of redness or orangeness or even whiteness where it's really, really bright. Okay? Now, these darker areas, this is false color. So that simply means it's an area of the atmosphere of the sun that's cooler than 60,000, roughly, 60,000 Kelvin. All right, now, it's up there in the atmosphere above the surface or the photosphere of the sun, which is 5,800. So it's kind of mysterious why it does this. We're still trying to work out why the atmosphere of the sun is so hot. But and here's just a side note. Angstrom is a 10 billionth of a meter. Here's another picture. This is like the one that we saw earlier, another false color. This is 171 angstrom, so go ahead and make a note of that. The blue ones are a false color in the 171 angstrom wavelength. So this is another filter. You put it in the front of your telescope, you snap your photo. But it's going to be an ultraviolet image. And so you assign computer-wise, a blue or maybe even a white right here. Now, check this out. Look at see that? The same area right here is bright in both images, but slightly different looking at this high temperature. So that's at about 1,000,000 Kelvin. Right? Now, this is a little bit higher up in the atmosphere. Here's 195 angstroms. Whoa, 1.5 million Kelvin. Right, now look at this. This is the bright spot over here. Still pretty bright. So whatever was happening that day, you can bet a lot of guys were eyeballing this little area on the right. And you can see different little areas of really, really hot temperatures. in the sun's atmosphere. So 195 angstroms, 1.5 million K. Here's another one. 284 angstroms, 2 million K. Whoa. And again, this thing is really hot. And notice how you're starting to get a really extended atmosphere. Now, the size of Earth is maybe, look at one of these little dots here. You know, Earth is going to be about the size of this little dot here. And Earth is pathetic compared to the SUN. Just is. I mean, it looks big to us, and it would take us a year to walk around the equator of the Earth. I mean, if you could walk, you know, the equator. But it's not, and the sun is enormously big compared to the Earth. All right, here's another picture of the sun. Okay, now this one is in 67, 68, so that's kind of reddish. Okay, 67, 68 angstroms. That would be 676.8 nanometers. And so this is reddish. It's a black and white image, so they take a red filter and they use black and white film to record this one. And so you can see where there's a lot of, you know, and here's this same bright spot over here. You know, so analyzing all these different temperatures and wavelengths, you're going to, you know, it'll reveal a lot about what's actually happening in the atmosphere. And then this would be in the photosphere at this level. I believe this will be the photosphere. This might be the chromosphere. I guess I should look that up. Anyway, let's get down to some business. So here's our question, our burning question of the day. How much hydrogen does the sun burn per second? Okay, here's a picture of a coronal mass ejection, CME, back in 2007. We had a pretty big one not too long ago, but it missed Earth. So if we ever get one of those, you know, full on, it's going to be a rough day in the neighborhood. Whichever side of the Earth is facing the sun when that thing hits, and they're pretty big, so the Earth is going to spin into it. So it's going to cover more than just half the Earth. It's going to be a bad day at the OK Corral. All right, so here, this is something we know, the solar constant. And that tells you how much energy per second per square meter at some imaginary sphere of radius 1 astronomical unit. So 500 light seconds out from the center of the sun, you're going to see this much wattage per square meter. All right. Now, if you work all that out, it works out to, as I said before, 3.8 times 10 to the 26 watts, which is the approximate luminosity of the sun. Now, we've already gone over that, and we're going to actually look at that a bunch of times today and the next few. I'm just looking at a couple guys in the very back. You athletes are supposed to be sitting up in the front. That used to be the rule. I'm looking at a guy, he's back there, he's got his beats on, he's just listening to music, he's not even listening to me. Yeah. Dude, I was just watching you for 5 minutes. You were just, you know, I didn't have your attention. But that's all right. It's your grade, not mine. Okay, so this is the source. If you did your reading, 11.1, Einstein's theory of relativity predicted this equation equals mc squared, one of the most famous equations in all of history. And it means that just any item, anything that has mass has a certain energy. It's like the energy of existence. But they conjectured very soon after that, if that's really true, can mass be converted into energy? And the answer to that is yes. The nuclear fusion reactions in the core of the sun transform gram by gram hydrogen, basically protons and stuff, into energy. So when you figure that out, for the sun's luminosity, so many watts, so many joules per second, it works out to 4.28 times 10 to the 9 kilograms per second that flow through this equation, equals mc squared. In other words, the nuclear reactions transform mass into pure energy at the core of the sun at this rate. It loses, and actually now that I look at it, this should be a minus. The change is negative 4.28 times 10 to the 9 kilograms per second. The sun is losing 4 billion kilograms per second. Approximately. That's 4 billion metric tons. 4.28 million metric tons, because a metric ton is 1,000 kilograms. Okay, this is 10 to the 9. So decrease that by 3, 10 to the 6. That's how many tons you are losing. All right, so let's take a look at this. All right, equals mc squared. There's our equation. Go ahead and make some room to take notes. And the speed of light here for c squared, that's 3 times 10 to the 8 meters per second. And hey, you guys, this is not a kinetic energy. This is a rest energy. It's not 1/2 mv squared, although it does work out to joules. C squared is 9 times 10 to the 8 meters squared per second squared. All right. And so this being the luminosity of the SUN here, here's the amount of energy, delta M times c squared, that is lost per second. Right? So that means that 3.85 times 10 to the 26 watts, actually that should be joules, divided by c squared is equal to delta M. Right, now this is a complicated, just jot the results down. I'll just trot through them with you. Okay, so here's the numerator, that's the luminosity of the sun. And here's joules, kilogram, meter squared per second squared. That's a mass times the square of a speed. And then down here, this is a square of a speed, the square of the speed of light. Meter squared per second squared. All right, so there's the square, there's c squared here, and here it is down here in the denominator. So we're trying to get delta M by itself. And when you calculate this out, you get 0.428 times 10 to the 10 kilograms per second. Or, as I said, 4.28 times 10 to the 9. So here's the luminosity. Let me just review this for your notes as you jot down these equations and then annotate your equation. 3.85 times 10 to the 26. That's the luminosity of the sun in all directions. You know, that's how many watts shine out from the entire surface of the SUN. And by the time it gets out to Earth's orbit, 500 light seconds away, it's down to 1,367 watts per square meter. But as you know, the total of it is 3.85 times 10. This is 385 octillion watts. A lot of wattage. Okay, now that's got to be equal to some E equals mc squared per second. That is how the fusion reactions work. And so this is how we figure out delta M. So here's the mass. This is the mass loss. Delta M This is how much loss in kilograms per second. All right, so it looks like 4.28 times 10 to the 8, excuse me, times 10 to the 9, 4.28 billion kilograms per second. You know, it's gotta burn out pretty fast, right? No, not really. If you compare this to the mass of the sun, which is 2 times 10 to the 30 kilograms, it's a teeny fraction. Teeny. All right, so let's take a look at this. So this is still how much hydrogen does the sun burn per second. So now we're doing this should be A and B here. We're on 2B. And we're going to figure out the fraction of the sun mass that is burned at this rate. Okay, so we're going to figure out how much of the sun's mass actually is 4.28 times 10 to the 9. Okay, so here's the burn rate. Okay, every second it loses 4.28 times 10 to the 9 kilograms. Okay, so here's the burn rate on top. Here's the total mass that the sun has got, approximately 2 times 10 to the 30. Dude, that's a lot of kilograms. That's way more than an octillion kilograms. I don't even know what that would be. 10 to the 24 is octillion. 27, 9 octillion. 10 to the 30 is 10 octillion. I don't even know what they call that. Anyway, here's your calculation here, right? 4.28 times 10 to the 9 divided by 2 times 10 to the 30, right? And that works out to about 2 times 10 to the minus 21 of the sun's mass per second. All right, 2 parts per 10 to the 21. Okay, 10 to the 21 is, let's see again, 1,000, million, billion, trillion, quadrillion, 5 trillion, 6 trillion. So this is like 2 parts per 6 trillion of the sun's mass per second. So it's not losing jack. All right. So in 1 year, the sun converts, so multiply this times how many seconds you have in a year, 31,536,000, and that's how many kilograms of its mass is converted into energy in a year. But that's not even, how many years can that go on? A whole bunch. 1.5 times 10 to the 13 years. All right, so that's using the total mass of the sun. And then down here, this in the denominator, that's how many kilograms it loses per year. Not per second, but per year. So, we got a real hot nuclear reaction. But we got a huge amount of mass. It's not burning so much that it's ever going to go out anytime soon. It's going to keep burning hydrogen until the cows come home. All right, now this is table 10.1 from your textbook. Okay, and make a note in your notes, table 10.1. Dr. B went over this March 1st. Here's the luminosity of the sun. 3.8 times 10 to the 26 watts. Here's its mass, 2 times 10 to the 30th. We've already used that. Here's a kind of a cool feature. The radius of the sun, 696,000 kilometers, about 109 times the radius of the Earth. So that's like when I was looking at those false color images of the sun in ultraviolet light, and I said, one of these little dots, that's the Earth. Yeah, that's what I was talking about, 109 times bigger. Okay, here's the approximate composition, mostly hydrogen and helium, a little bit of the heavier elements. Surface temperature, we've talked about that. Sunspots, About 4,000 Kelvin maybe. And that's why they look dark. They look like dark spots, but it's not like somebody threw some dirt in there to make it look dark, or it's because it's cooler, so it doesn't give off as much light. But it's still pretty hot. I mean, if you stuck your toe into a sunspot, sayonara to your toe. I mean, it's still pretty hot. Core temperature, 15 million Kelvin. Forget about it. And this is the condition that you need to undergo thermonuclear reactions. All right, now go ahead and make a note, figure 10.2. Dr. B thinks this is important because the energy released by fusion heats up all the surrounding gas. See, this is where the sun is fusing hydrogen here, this nuclear reaction, that's a fairly small part of the sun. It's down the core. Most of the sun is not fusing. All right, but enough of it fuses to heat the gas and then maintain outward pressure that balances the sun. So gravity's trying to shrink everything down, but then it's shrunk things down, Leland, enough that at the core, the heat will start nuking off thermonuclear fusion. Okay, and this is a quote from page 286. And here's another picture of it. Now, this is an important one for us because it tells you the different temperatures and zones of the sun. Now, we're going to talk more about this on Thursday, as well as some other calculations. Be ready. Make sure you start reading or finish reading all of chapter 11. No new homework. Finish what you've got. It's going until midnight, I believe. Is that right? It should be going until midnight tonight. Thursday. Okay. Yeah, finish what you got. You're dismissed. Yeah.